Have you ever found yourself washing spoons and noticed the water bounce off the spoon like this? Here we see that the water forms some interesting shapes. Sometimes you might see something that looks like a sheet, or maybe even a bubble. Let's dig deeper to see if we can recreate it and find out why it looks so cool. We'll run our first experiment with a test rig, a laminar flow source, and a baseline impactor. Here we see that if the water hits the impactor at a high flow rate, the water will shoot outwards like a sheet. While gravity plays a small role here, causing the water to bow downwards at the ends of the sheet, the flow rate is high enough to overcome this gravitational force and continue to travel outwards. A decrease in the flow rate results in an interesting change in shape. While some may expect the water to fall on a more parabolic trajectory, we can observe that the water begins to sag quite a bit due to gravity. Here the sheet closes on itself, forming our first observable water bell. Here we can see an inverse relationship between the radius of the impactor and the radius of the water bell. But what is happening to cause the water to form this bell shape? The top half of the bell seems to intuitively make sense. The gravity pulls the water down, forming the parabolic curve, but why is the water pulling back inwards towards the impactor in the bottom half? We must consider how gravity, surface tension, and the movement of air inside the bell help to form the shape. As the exiting water off of the impactor is now smaller in velocity due to the lower flow rate, it is more susceptible to the effects of gravity. The surface tension acts along the curve of the bell both on the inside and outside layer of the water. These surface tensions generate a resulting inward force, which begins to pull the bell back into the center, closing the sheet. Furthermore, the movement of the curved sheet of water generates a circular motion of air that is trapped inside the fluid sheet, which forms a region of lower pressure, inducing a pressure difference between the high pressure outside, contributing to the inward force. When changing the impactor shape, the water bellows out in a slight conical shape due to the angle of the impactor, forcing the water downwards. The sheet forms a cylindrical wall around the impactor, but we do not observe bell-like behavior. When introducing a cone-shaped hole into the top of the impactor, we see the water begin to shoot upwards, forming a dome, eventually breaking down into small droplets.